So dear students, in the last class, we had talked about the frequency modulation. We had seen that frequency modulation can be generated in two ways. One is direct method and another is indirect method. So in today's class, we will mainly focus on the demodulation part of FM signal, and you will be able to appreciate the demodulation part, and it will be interesting also in a way that you will be able to again correlate your mathematics with your physical concepts. Again and again, I am emphasizing this point from day one, that mathematics will help us or will save us from nitty gritties of the system directly. So first we will clarify our concept in terms of mathematics, and then we will try to correlate the understanding of mathematics with our actual physical system, and you will get a feel of that thing in today's class as well. So the demodulation part of FM, what I feel is quite interesting, and it will utilize the concepts that we have already studied in our previous classes or previous semesters, and I hope you will enjoy the content of today's class. Next. So this is just a quick review of what we have discussed in FM generation. So in FM generation, I told you that we need a voltage variable output frequency. Okay, we need a frequency that is proportional to variable voltage. Okay, and what we have done, we have taken an LC oscillator tank circuit whose inductance or capacitance is varied, and that variation in inductance and capacitance has been made proportional to the voltage. So as a result, we get voltage variable reactance which is placed across our tank circuit. This is what we had discussed. And then we saw that voltage variable reactance can be obtained by using your varactor diode, your field effect transistor, and your BJT. And as I told you, that FM can be generated through two methods. One is your direct method and another is your indirect method. And we have studied both the methods, that how can we generate FM with the help of direct method and your indirect method. So today we are going to discuss the FM demodulation part from the next slide onwards. So FM demodulation. So students, we all know what is the meaning of demodulation. In demodulation, we want to recover our information signal back. Okay, so this was our modulated signal or FM signal, and in demodulation, we will be recovering our information signal back from that FM signal. Okay, and obviously our original information signal was a low frequency message signal that was clubbed with the carrier to give us the modulated signal. So reverse process will be carried out in FM demodulation. And since we are talking about FM demodulation in particular, and we know the concept of frequency modulation. So in frequency modulation, what we do, we convert amplitude changes into frequency changes. So now in demodulation, reverse will happen. So in case of FM demodulation, we have to convert our frequency to the amplitude. So that's why your FM demodulator can be called as frequency to amplitude changer. So more precisely, if I talk about FM demodulation, it means that the frequency deviation of the incoming carrier is converted into amplitude variation of the audio frequency signal. I hope all of you have been able to understand this. We have changed the frequency of the carrier, means our information is present in terms of the change in frequency or the frequency deviation. And that frequency deviation we have to now convert to the amplitude variation of the audio frequency signal. So that is another way to describe point number one, that is we have to convert our frequency deviation to the amplitude variations. Okay, now one thing that we have to keep in mind or take care of while converting frequency changes to amplitude changes, that this conversion, it should be efficient and it should be linear. So this linear part is very, very important. So students, in FM demodulation, the main problem that we will face is we will be able to convert frequency changes into amplitude changes, but ensuring the linearity while converting frequency to amplitude changes is very, very important, and it's not easy also. So that's why in different methods, as we move from one method to another method, our aim will be to ensure linearity as far as possible. Okay, that is point number one that we have to take care of. Second point that we have to take care of is that our FM detection circuit or FM demodulation circuit, it should be insensitive to the amplitude changes. So if you remember, our information content is present in the frequency changes only. We do not have incorporated any information in the amplitude variation. Okay, so originally in FM signal, our carrier part was constant. Okay, there was no variation induced by the modulating signal into the carrier. So that's why if some amplitude changes have taken place into FM signal in the channel, then those amplitude changes, those are spurious signal. Okay, so we cannot allow those spurious signals which have done amplitude changes in the carrier of FM signal, we cannot allow them to come into our final output. So that's why our FM detection circuit, it must be insensitive to the amplitude changes, or in other words, I should say that the amplitude changes, if any, in the carrier or FM signal, they must be, ignored, or they must be discarded. Okay, so now what is the main crux of FM demodulation? So students, you'll be very surprised to have this concept that in case of frequency modulated signal, we will convert our frequency modulated signal first to amplitude modulated signal. Okay, and then your amplitude modulated signal will be demodulated. So in a way, we will convert our FM signal to AM signal, and then we know the demodulation of AM in detail. We have already discussed. So here you can keep this thing in mind that your frequency modulation has to be converted to amplitude modulation, and then amplitude modulation will be demodulated using diode detector that we have already seen. I hope all of you have been able to understand this point, and it will be further clarified in the coming slides. Okay, so the main concept that we will use for converting FM to AM is your slope detection. So with this terminology of slope detection, now we move forward. So the first kind of FM detector or FM demodulator is called basic slope detector. So by using slope detector, we will be able to demodulate FM signal. Okay, so as I told you, in FM demodulator or in basic FM demodulator, we are going to convert our frequency deviation of the incoming carrier into the amplitude variation. And I just told you in the previous slide that your FM will be converted to AM, and then finally it will be converted to the demodulated signal. So now how do we do that? Or how does our basic slope detector work? Okay, so students, all of us have understood or studied the concept of filters. All of you know the working of LC filter. So in LC filter, we have an inductor, okay, and then we have a capacitor in parallel, okay. So if it is a filter, then what happens? What does a filter do? In case of a filter, your signal enters into the filter, and depending on the resonant frequency of this LC filter, a given frequency is passed through. Okay, so if the frequency of the incoming signal lies in the pass band of this filter, then that frequency is passed as such, and if the frequency is different, then that signal is attenuated. Okay, so let me explain this thing in more clear fashion. Okay, See, how does a filter behave? Say, this is my incoming signal having certain frequency. Fine. And if I pass it through a filter, and if this incoming signal frequency lies in the pass band and say exactly equal to the resonant frequency, then this filter will pass this frequency as it is, means the same frequency and the same amplitude. This is the output of the filter if the input signal frequency lies in the pass band. And in fact, I'll go one more step ahead, that if this frequency is the resonant frequency of the filter. Now what happens if my filter resonant frequency is different from the incoming signal frequency? In that case, the output of that filter will be attenuated, or this frequency will be attenuated. Very small output will be obtained if it is not exactly equal to the uh, resonant frequency of the filter. I hope you have understood this concept. What I want to say is that if the incoming signal frequency is equal to the resonant frequency of the filter, then the output will be maximum. Okay, maximum means it will be equal to the input signal frequency. And if my filter resonant frequency is different from the incoming signal frequency, okay, then in that case the output signal amplitude will be attenuated, or it will be reduced. Fine. So what I want to make a point here is that as we deviate from the resonant frequency, the output amplitude or the output voltage of the signal, it changes. Okay, so all of you know the resonance curve. How does it work, or how does it look like? Let me explain here. So your resonance curve looks like this. Fine. And the peak indicates the resonant frequency. So this is our resonant frequency, and say this resonant frequency is F naught. Okay. So at the, and this is your output voltage, say V naught. And on your x-axis, we have frequency. So at the resonant frequency, what do we have? We have the maximum output possible at the resonant frequency, if I pass the resonant frequency. And if I pass this frequency, say, which is away from the resonant frequency, but it lies in the pass band. If I say this frequency, say F minus, in that case, for this F minus, the output will be less. This will be the output voltage, some V dash or V minus. Okay. Similarly, on the other side of my resonant frequency, same thing will happen. Again, my output will be reduced if I move in the positive direction of the center frequency, that is your resonant frequency. So try to understand here what is happening. I am changing the frequency of the signal. As I move away from my resonant frequency, at resonant frequency, I am getting maximum voltage. On the either side, if I go towards left hand side of my resonant curve, then as I move away from the center frequency, my amplitude is reducing. Okay. And if I come back in the reverse direction, then my frequency is increasing and my amplitude is also increasing. Similarly, in the other side, same kind of trend is obtained. So what I want to say here, that in a resonant circuit, we get maximum output at the resonant frequency. Okay. And then that output is changing on the either side of the resonant frequency. Okay. So that means that your resonant frequency curve is giving you some amplitude changes with respect to some frequency changes. On x-axis we have frequency, on y-axis we have amplitude. Okay, so as your frequency changes, your amplitude changes are induced. This is how your filter work, and same concept we are trying to use here. So we are changing the frequency. As a result, we are getting the amplitude changes. Okay, so that means with the help of this resonant circuit, we are converting our FM to AM. Now the question is, why are we calling it as slope detector? See, at the center of resonant curve, we have our resonant frequency. So if you concentrate only on the one side of resonant frequency, fine, we have a slope. Okay, so this slope is basically changing on the one side of your center frequency. Fine. So we have to detect our amplitude changes with respect to frequency changes during this slope. Okay, that's why we are calling it as a slope detector. Fine. So we will not work at the centralized resonant frequency. Okay, we will work on one of the sides or one of the directions of center frequency, and we will try to detect that slope. Okay, let me redraw the figure so that you can again understand this thing clearly. Okay, so this is our slope. Fine. If I take this portion of this slope and I keep one midpoint, then on either side of this midpoint, okay, if I go towards left hand side of this midpoint, my slope is coming down, slope is decreasing, and on the right side of this, my slope is increasing. Okay, so this is what has been written in the slide also, that in case of slope detector, basic slope detector, what we do, we take a tuned circuit. Tuned circuit means it will be tuned to a certain frequency whose resonant frequency is to one side of the center frequency of the FM signal. Okay, what does it mean? It means that we have to take such a tuned circuit. Obviously, this is resonant curve. This is the resonant frequency. Okay, so obviously, since it is a tuned circuit, fine. So this resonant frequency is indicated by, say, F naught, and then since we are using FM signal, let us assume that my center frequency of my FM signal, that is carrier frequency FC, is on the one side of my resonant frequency. Okay, so this is how we maintain this carrier frequency on the one side of my resonant frequency. Fine. And now if you see that if I go on the either side of the center frequency, my amplitude is decreasing or increasing. Okay, so in this case, your output of the tuned circuit during this portion, it will be proportional to the frequency deviation. On x-axis, we have frequency deviation, that is delta F. Okay, and on y-axis, I have amplitude changes, that is my delta V. You can very clearly see here. So what I am doing here, that your output amplitude of the tuned circuit is proportional to frequency deviation. That means amplitude modulation has been obtained. Okay, so one figure has also been shown on your slide towards left hand side, which will further clarify what has been explained to you. You see, this is our resonant curve. This is our resonant frequency of the circuit. This A point is nothing but our center frequency of the FM signal, that is carrier, okay, which has been our carrier frequency and labeled as FC. Fine. And obviously my signal frequency will be changing on both sides of FC. It will be either FC plus delta or FC minus delta. So this is my frequency deviation at the bottom. This is my frequency deviation, and this is my center frequency. Okay. And this is my output voltage. So as my frequency deviation is decreasing as I move in this direction along with this sinusoid. So if my frequency is changing, my amplitude changes are taking place. So this peak, it has come here, this peak, and this peak, it has come here. Okay, so your frequency changes have been converted to amplitude changes. Okay, or frequency variation has been converted into amplitude variation. Okay, and this amplitude variation has happened with carrier. Okay, this output voltage is the output voltage of the signal which is coming out. And which signal is coming out? The signal centered around carrier frequency is coming out, and see, its amplitude is changing. Okay, and you can see this output waveform. It is nothing but it is the envelope of your carrier. Okay, and which can easily be demodulated with the help of your diode detector. So your output voltage, which is nothing but your envelope signal, AM envelope signal, that can be applied to a diode detector, okay, along with RC, and we get the demodulated signal back. Fine. So this is the main concept of my slope detector. So I hope all of you have understood, and you must have found this thing very interesting, that how actually we have utilized the concept of filter in demodulating our FM signal, and how actually we have detected the slope. And students, let me tell you one point here, though it is very simple and its name is basic slope detector, but there are certain issues, and those issues are, one is linear or linearity. I told you in the previous slide also. See, we all know that whenever we say that my curve is linear, it means it follows a straight line path. Okay, but if you see here carefully, that my resonant curve, it is not a straight line, it is following a curved path. Okay, and if you consider this curved path on my resonant curve, you see that there is only a very small portion that can be approximated to a straight line. Okay, so see, if we have straight line path, only then my frequency deviation will be converted to amplitude changes in a perfect manner, or in a directly proportional manner. Okay, otherwise there will be some deviation. So that's why we should seek for more and more linearity on my resonant curve. Okay, and another problem with the basic slope detector is that this slope detector not only reacts to the frequency changes, but it also reacts to the amplitude changes. If the amplitude of incoming signal is high, then the corresponding amplitude of output signal of the tuned circuit will also be high. So that indirectly means that your amplitude changes have been taken into account in this slope detector. So these are the issues which will be further taken care of in the coming circuit. So I hope all of you have been able to understand up to this point, and now we will move to our next topic. So students, after basic slope detector, we now move to balanced slope detector. I told you in the previous slide that your basic slope detector is very simple, and it gives us a path to understand the advanced circuit of FM demodulation. but your basic slope detector, it suffered from the problem of non-linearity, because your basic slope detector was linear for a very limited range. So that problem has been taken care of up to certain extent in your balanced slope detector. So your balanced slope detector is, in a way, you can say, advanced version of your basic slope detector. So this balanced slope detector is also called as Travis detector. This is another name for this balanced slope detector. Okay, so if you look at the circuit of Travis detector or balanced slope detector carefully, you will observe that this is again more or less similar to your basic slope detector. Okay, but a few additions have been made here. So if you look at only the top portion of this balanced slope detector, and if you concentrate only on the top portion, this is nothing but your basic slope detector. So in balanced slope detector, what we have done, instead of, you can say, one basic slope detector, we have taken two basic slope detectors. Okay, as I told you in the previous slide that we will have LC circuit, which is a tuned circuit, tuned to a certain frequency. Then I told you that we will have a diode as envelope detector. Then we will have RC, resistance and capacitance. Okay, so your upper portion was only in the basic slope detector. In balanced, we will have two such circuits. Okay, so in case of balanced slope detector, the circuit uses two slope detectors, and these slope detectors, they are connected 180-degree out of phase. That is very, very important point. Okay, so let us see how actually they have been connected 180-degree out of phase. See, we have used center tapped secondary, center tap transformer. So in the center tap transformer, your voltage will be induced like this. That is your plus minus and plus minus. So if you look at the two ends of this secondary, so your diode D1 will be subject to the positive polarity from this side, and diode D2 will be subject to the negative polarity. That's why your uh, two parts of circuit have been called connected 180-degree out of phase. That is one thing. Okay, and another thing, as I just told you, that your each of the tuned circuit, both the tuned circuits, they are connected to diode detector, means there are two diodes and RC load. So each diode is connected with a combination of resistance and capacitance separately. Okay, and we know that diode is a single direction device. So in the upper portion, your current flows from upward direction to the downward, and in case of the lower part of the circuit, through your diode D2, your current flows from the downward direction to the upward direction. So if you look at the output voltage is proportional to the difference of the voltages or difference of the currents which have been passed through the two diodes. Okay, that means the output of the two slope detectors, that is subtracted, and then the finally output has been obtained. So subtraction indirectly again emphasizes the point that the two detectors are 180-degree out of phase. Okay, next. So as I told you in basic slope detector, that we used our slope detection concept, means your resonant frequency curve of the tuned circuit. Okay, and since now here there are two slope detectors in reverse direction, so this is, say, one slope detector for D1. Now another slope detector will be in reverse direction. So for that, your resonant frequency, it should be in reverse direction like this. Its curve should be in reverse opposite. Okay, so this will be, you can say, output of your diode D2. So if you precisely combine or precisely consider their resonant frequency and combine them, then this is what you get. Look carefully at the left hand side of your slide. So we have merged the two parts of the circuit in such a way, their frequencies have been adjusted in such a way that these two resonant curves, they take the shape of S. See, this is S. That's why we call it as S-shaped frequency modulation characteristic. Okay, and we call it as balanced slope detector, means the two slope detectors, they are balanced. They are balanced means they are exactly opposite of each other. The two circuits, they are exactly opposite. They are balancing each other. So that's why we are calling it as balanced slope detector. Fine. I hope all of you have understood this. And this S-shaped frequency modulation characteristic has only been obtained by balancing the two. And why have we done this thing? The main reason behind obtaining this S shape is to increase the linearity range. Now, you see, the range of linearity, it has become almost double to that of your original basic slope detector. Okay, and if you your adjust curves like this, you can again see that your straight line portion between these two uh, resonant curve, that has also increased. So we have increased the linear frequency range by using balanced slope detectors, or by combining two slope detectors in 180-degree out of phase. Okay, so that is the main advantage of this balanced slope detector. You can clearly see that your straight line portion is much larger in case of this S shape as compared to your simple basic slope detector. If you draw S carefully, obviously you make it a hook like this, and this is your straight portion that you have increased. Fine. I hope all of you have understood the concept. Rest, how actually slope detection works, that we have already discussed. Now, let us see the working of this circuit. So what we do in the transformer, we all know that there is a primary part and there is a secondary part. So your primary part is tuned to your center frequency of the FM signal, that is your carrier frequency. Then we have center tapped secondary in the transformer. So the upper portion of this secondary is tuned to FC plus delta F, and the lower portion is tuned to FC minus delta F. Now you see here the point where the two resonant curves will be meeting, the center point of these two, that will be equal to FC. Okay, and this upper resonant curve in the positive direction, the resonant frequency is FC plus delta F, and the lower portion of the circuit has resonant frequency equal to FC minus delta F. Okay, and this is our FC. So here you can see that your transformer is tuned corresponding to three frequencies. So primary is tuned to FC, and secondary is, the two portions are tuned to FC plus delta F and FC minus delta F respectively. So there are three cases: FC, FC plus delta F, and FC minus delta F. Now, so your incoming signal obviously will come from the primary of the transformer. So if your incoming signal is equal to the carrier frequency, okay, your say carrier is coming without any modulation, then what will happen? In that case, your upper tuned circuit is tuned to FC plus delta F, means this is the resonant frequency and this is the incoming frequency. So in this case, the gap from incoming frequency FC to the tuned frequency of upper circuit, that is same as the gap of incoming signal frequency from the other portion, that is FC minus delta F. In other words, your incoming signal frequency FC is having same gap from FC plus delta F and FC minus delta F. Okay, that means the upper tuned circuit and lower tuned circuit, they will give exactly same output, and they will be that will be subtracted, and obviously the output in that case will be 0. So here this small f represents the incoming signal frequency. So if the incoming signal frequency is equal to carrier frequency, my output will be 0. I hope all of you have understood this. Now what will happen if my incoming signal frequency is equal to, so let us assume this incoming signal frequency is equal to fc plus delta f. Okay, in that case, what will happen? So if my incoming signal frequency is equal to fc plus delta f, it means we are having the incoming signal frequency equal to the resonant frequency of the upper portion. It means the upper portion of the circuit will give the maximum output because it is a resonant frequency of the incoming signal. Fine. And what will be the output for this second portion of the circuit? This second portion of the circuit, since this frequency is the incoming frequency, for this upper portion will give maximum output, and this fc plus delta f is very, very far away from the resonant frequency of the lower portion. So that's why it will give the minimum output. So diode D1 will give us maximum output when my incoming signal frequency is equal to fc plus delta f, and diode D2 will give me minimum. So what will be the output? Output will be the net positive maximum. Okay, so what does it mean? When my input signal frequency is say maximum at fc plus delta f, then my amplitude is also maximum. And reverse happens when my incoming signal frequency is equal to fc minus delta f. Then what happens? In that case, my lower portion of the circuit, it will give me maximum output, but that maximum output will be in negative direction, means this one. My incoming signal frequency is this. Corresponding to this frequency, my second portion of the circuit will give me maximum output in the negative direction. But this fc minus delta f frequency, it is very far away from fc plus delta f. As a result, the output of fc plus delta f portion will be, you can say, minimum. So your positive portion is minimum here, okay, and negative portion is maximum. As a result, the net output will be negative maximum. Negative maximum. So what does it mean? That if my incoming signal frequency is equal to fc minus delta f, then I'll be getting the most negative amplitude. So I hope you have been able to understand that how actually the frequency of the incoming signal is being converted into the amplitude changes. Okay, and those amplitude changes, they have been, their envelope has been detected back with the help of this diode and RC. Okay, so this is how our balanced slope detector works, and this is how your firstly FM changes have been converted to AM changes with the help of tuned circuit, and those AM changes have been demodulated with the help of your diode detector circuit. Okay, so you can see that balanced slope detector achieves more linearity as compared to your basic slope detector. Now, it doesn't mean that balanced slope detector is totally issue free. There are some issues in balanced slope detectors as well. And one such issue is that we have three frequencies to align. See, students, we say that there is a resonant frequency, and at resonant frequency we have maximum output, but uh, your tuning circuit at a given resonant frequency is very, very difficult. Okay, or you can say aligning your circuit to some center frequency is very, very difficult. So here we have three frequencies to align to. Your primary, it should be aligned to fc. Okay, your secondary, the upper portion, it should be aligned to fc plus delta fm, delta f, and your lower portion of your secondary, it should be aligned or tuned to fc minus delta f. Okay, so this is very, very trickier and a bit difficult also to align to three frequencies. Okay, so still we have been able to achieve more linearity in case of balanced slope detector. And the problem that we had in basic slope detector, that is circuit reacted to amplitude changes, so same problem still lies in balanced slope detector as well, that we do not provide amplitude limiting in balanced slope detector. So if there are some amplitude changes, your balanced slope detector will react to those amplitude changes also. So in balanced slope detector, we have been able to rectify one issue, that is increase in the linearity of your circuit, but amplitude limiting part is left. So this is about your balanced slope detector. So students, after this balanced slope detector, we move to our next topic, that is your phase discriminator. Okay, and though this phase discriminator is also, not free from all the issues, but as we are moving from one kind of circuit to another kind of circuit, and we are removing whatever issues or challenges are there in an incremental way, similarly your phase discriminator is also a circuit in that direction. So this phase discriminator circuit is also known as Foster-Seeley discriminator. And this circuit has been derived from nowhere else but your Travis detector, that is your circuit that we discussed in the uh, last few minutes. Fine. And as I told you that this circuit provides us the same S-shaped response curve as we saw in Travis detector. So obviously, since we have S-shaped response curve, so we have large linearity range. Okay, now what is the change from the previous circuit? If you remember, I had told you in the previous circuit that my primary and secondaries together, they need to be aligned to 3 frequencies, and which was a difficult task. So in our phase discriminator circuit or Foster-Seeley discriminator, we are removing that limitation. So in case of phase discriminator, the main advantage that we get is that my primary and secondary winding both, they will be tuned to single center frequency of the incoming signal. So instead of 3 separate frequencies tuning as we required in previous circuit, as I'm just showing you, that is FC, FC plus delta and FC minus delta. Here in phase discriminator, all the windings in primary and secondary, they are tuned to a single center frequency. Okay, so this phase discriminator circuit, if you look carefully, then many things, they have been taken in a similar fashion as it was in Travis detector, but there are certain portions which are totally different also from Travis detector. So you can see the circuit of this phase discriminator or Foster-Seeley discriminator on the left hand side. Okay, so let me tell you where are those changes. One change is that this inductor L3 has been added here, which was not there previously. Okay, another change that has been included is that this is your coupling capacitor C has been included in between your primary part and your secondary part. So primary and secondary windings, they have been connected with the help of a coupling capacitor. Okay, and rest of the things, see, D1 D2, they are same as in Travis detector. Then your R3 C3 and R4 C4, they are also exactly same as it was there in Travis detector. Similarly, your L1 C1 and your center tapped secondary along with your tuned capacitor, that is same. Okay, so these are the few changes that have been highlighted here in the circuit of phase discriminator. So if we look at this circuit directly, then this circuit seems to be a complex circuit as compared to our balanced slope detector circuit. But we will try to understand this circuit in parts, and then you will realize that how simple it is to understand this circuit. Fine. So we will try to understand the working of this circuit mathematically. So that's what I wanted to point out in the initial time of this class, that with the help of mathematics, we will prove the operation of FM demodulator circuit. So that circuit is nothing but your Foster-Seeley discriminator. Okay, so here what we want to prove with the help of mathematics, we want to prove that the voltage applied to each diode, we have two diodes. First, say we take diode D1. So the voltage applied across this diode, okay, across this diode means at the two ends of this diode, the voltage across this diode is the sum of the primary voltage. What is the primary voltage? That is V12, and the corresponding half of the secondary voltage. How much is the secondary voltage? That is VAB. So mathematically we have to prove that the voltage across diode is the sum of the primary voltage, that is V12, plus 1 by 2 VAB. VAB is nothing but the secondary voltage. So mathematically we have to prove this. I'm telling you this thing beforehand so that you are able to correlate what we are trying to do in the coming slide. So this is one thing that we have to prove, that voltage across diode is the sum of the primary voltage and your corresponding half secondary voltage. Okay, so that we will see in the next slide. Another thing that we have to see in our mathematical analysis, or we have to prove, that your primary and secondary voltages, I just told you our primary voltage is V12 and our secondary voltage is VAB. The secondary and primary voltages, they are exactly 90° out of phase. 90° out of phase means if I represent my voltages with the help of vectors, okay, say this is my primary voltage, say V12, and this is my, say, secondary voltage VAB. Okay, so these are exactly 90° out of phase. There is a 90° phase relationship between the two when your input frequency is FC. So if the incoming signal frequency to this primary is equal to carrier frequency, then we have exactly 90° phase. This we have to prove. Second thing is, if my input signal frequency is higher than FC, means greater than FC, in that case they are less than 90° out of phase. Less than 90° out of phase means the phase angle between these two voltages, it will be less than 90°. Okay, means it will be 90 minus theta. Okay, and the third thing that we have to prove is, when your input signal frequency is less than FC, in the second point it was greater than FC. So when your incoming signal frequency is greater than FC, then we have 90°, less than 90° out of phase. Okay, and when your incoming signal frequency is less than FC, then your phase is more than 90. That means the two vectors, they are out more than 90° out of phase. Okay, so means this phase angle is 90 plus theta. So I hope you have been able to understand. So we have to prove these things mathematically. First is the sum of these two voltages, primary and secondary, and then the phase relationship between your primary and secondary voltages depending on the incoming signal frequency with respect to our carrier frequency. So I have summarized the complete concept of your Foster-Seeley discriminator. Now we will see one by one all these concepts. I hope you will enjoy this. Next. So first we concentrate on the first part. Before we prove that the voltage across diode will be sum of primary voltage and secondary voltage, half of the secondary voltage. We need to prove that VL is equal to V12. What is VL? See, I told you that one extra inductor has been incorporated in this circuit. So this VL voltage is across this L3 inductor. Okay, so now our objective in this slide is to find out the voltage across this inductor. Fine. So there is one more thing in the circuit that has been incorporated, or in fact that has been, you know, assumed, that the resistances which are present in the load, they are much larger than the capacitive reactance. That means the value of the resistances R3 and R4, they are very, very high as compared to the capacitance C3 and C4. Means since R3 and R4 are very, very high, so they will behave almost like open circuit. Okay, so now what we have to do here is we have to obtain the voltage across inductor L3, that is VL. Okay, so for that I'll redraw this circuit, this portion of the circuit. Okay, and how am I doing that? See, V12, this is the input voltage V12. Then this V12 is across C1 capacitor. This is C1 capacitor. C1 capacitor is in parallel with inductor L1. So this is our inductor L1. Okay, and we know that inductor cannot be, you know, pure inductor. There will be some resistance R1. So this inductor L1 has been replaced with R1 plus L1. So R1 is some, you know, inbuilt resistance, not exclusively connected. So this portion is nothing but it is exactly same, the primary part, except this C part. So we have this L1 parallel with C1 and V12 applied. I hope you understood this. Now at the output of this one end of C1, we have connected C. So here we have connected this C part, this coupling capacitor. This coupling capacitor is connected through this you know, center tap to L3. Okay, so this coupling capacitor is connected to L3 directly. I just show you. So this C is connected to this L3, and through this L3 then we move to C4 and then we go to ground. Okay, and this is also ground. So let me show you once again. This portion of the circuit is the redrawn portion for this V12, which is connected to C1 and L1. So this is your primary part, which has been shown here. One end of the C1 is connected to C, then L3, and then your C4, and then ground. And this is ground, so you can say this is how you connect it. So this portion of the circuit has been redrawn here. So this is your C, L3 and C4, and which is connected here. I hope all of you have been able to understand this. Okay, so now let us analyze this circuit. It is very, very simple. So we have V12 appearing in parallel across C1, then across R1, L1, and same V12 is appearing across this C, L3 and C4. So there is V12 appearing across this. Okay, so we have V12 across the series combination of C, L3 and C4. And we know voltage divider. So this V12 voltage is dividing across C, L3 and C4. So when we apply voltage divider for this VL, that is voltage across L3, so we have V12 into this impedance of L3, that is ZL3, divided by the total impedance of this series combination, that is ZC, ZC4, ZL3. Those have been added together. Okay, and we know that how do we represent the impedance or the reactance of a capacitor or inductor. So we know that since your L3 is ZL3 is inductor, so that's why it has been represented as J omega L3. V12 has been shown here, and your ZC is nothing but minus j by omega c. Your ZC4 is nothing but minus j omega c by 4. Your ZL3 is nothing but j omega L3. Okay, so it means we have VL equal to this one. Okay, and now another thing here is that this inductor L3 is an RF choke. RF means radio frequency choke. Okay, choke means coil. So this value of L3 is purposely given a very large value. So since the value of L3 is large, that means the reactance of this L3 will be very high as compared to this capacitive reactance. Okay, so that's why we can ignore this capacitance part. So if we ignore this, you can say that j omega L3 in the numerator, j omega L3 in the denominator, they will be cancelled, and we can say that your VL is approximately equal to V12. Okay, so that means the voltage across this inductor L3 is same as the voltage across your primary. Means your primary voltage has been brought inside the secondary through L3. This is what we wanted to prove here, that your primary voltage has been brought inside the secondary portion. Okay, so I hope all of you have understood this thing. So students, after proving that the voltage across this inductor is approximately equal to our primary voltage, now let us move to next part. So our next part is now to concentrate in the secondary part. Okay, so you look carefully in the figure which has been shown as A, and A figure is towards left hand side of this red line that I have just drawn. So here if you look carefully, so your primary is this one. Okay, and from primary your some voltage is induced in the secondary part, and which has been shown as L2, R2 and C2. Okay, so you see here that your primary is having L1 and your primary is nothing, secondary is having L2 and C2 in parallel. So same thing has been drawn here. Okay, so we know that see in the previous slide I had taken L1 as R1 plus L1. So that R1 was, you know, some negligible resistance that was shown to just have you awareness about the presence of some series resistance. Otherwise that resistance is negligible resistance. Okay, and we know that as some current flows in the primary, because of mutual inductance, current will be induced in the secondary coil. Okay, so same concept has been used here. See, your current which is flowing through the primary part, that has been taken as IP, and that current is equal to I is equal to V by R or V by Z. Okay, so in the primary we have only the inductive reactance, so that's why the voltage in primary is V12 and your impedance is j omega L1. So this is your j omega L1. So my primary current is given by V12 by j omega L1. Okay, and now since we know that because of mutual inductance or because of the current flowing in the primary, some voltage will be induced in the secondary. So that induced voltage in the secondary has been shown as a series voltage source in the secondary, that is Vs. And this series voltage source will be having a value that is equal to plus minus j omega MIP. M is what? Mutual inductance. Okay, and IP, since we know that V is equal to I into Z. So IP was primary current and j omega M is equivalent to your mutual inductance. So your Vs is equal to plus minus j omega M into IP. And this whether sign will be plus or minus, that will depend on the direction of winding. Otherwise, numerically, your Vs is equal to j omega MIP. So here in our analysis, we consider the negative sign. So we take Vs is equal to minus j omega MIP. And here we have obtained the value of IP. So we substitute this value of IP and we get Vs is equal to m by L1 into V12. Okay, so this is our value of Vs. Now here, what is our objective? Our objective is to find out the value of secondary voltage, that is VAB. This is our secondary. So our secondary voltage is VAB. Okay, voltage across secondary. So same, this secondary has been drawn in different fashion to make you understand the things. Okay, so your L2 secondary coil has been shown as series combination of L2 and R2. This is our induced voltage from the primary, and we have C2 in parallel. So if we want to find out VAB, that is voltage across secondary. Okay, so you see here that this VAB is equal to is calculated like this. See, this secondary coil has again been shown like this. Okay, so same thing redrawn. I think you are able to see that this circuit and this circuit, they are one and the same thing. All that we have done is your VAB is the voltage across C2, same thing, and then rest of this portion we have redrawn like this, just to make things more clear. Okay, so from here you can see here that this voltage VAB can be obtained by dividing by applying voltage divider law. Okay, so you can say that if Vs is the voltage, then this Vs voltage by voltage divider can be obtained equal to your voltage across this C2. So this is what we are doing. This VAB, that is voltage across C2, is equal to this voltage Vs, okay, divided across these three components of the circuit, which is nothing but voltage across impedance of C2 is ZC2, and then these three components are in series, so that's why in denominator we have ZC2 plus ZL2 plus R2. Okay, and we know what is ZC2 since it is a capacitor, so we have minus JXC2. Okay, what is Vs? We have obtained Vs in the above expression, this one, that is m by L1 into V12. So this is m by L1 into V12. Minus sign we have taken, so same thing has been taken here. Okay, so this is your Vs, this is your ZC2, and in the denominator what do we have? We have R2, that is resistance, and then since we have inductor and capacitor, we have complex iota present in it. Okay, so here we have J XL2 minus XC2. Okay, and we can represent this XL2 minus XC2 as X2 also. So in short, you can write this as R2 plus J X2. Fine. So what we have done in this slide, we have obtained or we have expressed the secondary winding voltage VAB. So this VAB is equal to Jm upon L1 into V12 into X2 by R2 plus JX2. In other words, I can say here that we have expressed secondary voltage VAB in terms of primary voltage, that is V12. So V12 was our primary voltage. So that is another thing that you should notice here. I hope all of you have been able to understand the derivation of this secondary voltage. Fine. So students, after obtaining this value of VAB, now let us move forward. See, this is what we have obtained in the previous slide. Okay, and in the previous slide we had a small mistake that your upper terminal of the secondary, it should be labeled as VA, and the lower terminal should be labeled as B. Okay, so we have obtained VAB in terms of V12. That was our outcome of previous slide. Okay, so this is what we have obtained. Now what we want to find out, we want to find out the voltages applied to D1 and D2. So if you look at this circuit carefully, how much is the voltage across voltage applied across D1? So D1 is connected here, okay, and your D1 is connected here, okay, through this you can say resistance up to this part. So voltage across this D1 is your VAO. Okay, this is your VA and this is your VO. Okay, so your voltage has been applied, which is represented as VAO. Similarly, voltage across diode D2 is nothing but VBO. Okay, VBO, voltage across this D2. Fine. So now we need to find out what is VAO and what is VBO. What is VAO? Let me erase and then you will be able to understand. What is VAO? Means the voltage across these 2 points in this upper portion of the circuit. So if you look at this circuit carefully, your VAO, it is having two things, this D1 and R3 in parallel with your this half secondary and this inductor. These are in parallel. So it means the voltage is same across these two. Okay, so from here you can see that your VAO is equal to VAC. AC is the half secondary, okay, plus VL, that is voltage across this inductor. Similarly, what is VBO? VBO is the voltage across the sum of voltage across this half secondary, that is VBC plus VL, means this inductor is common. Okay, now what is VAC? That is half secondary voltage, that is half of VAB. And what is VL? VL is V12. If you remember, we had proved in the previous slide that your voltage across this RF choke was VL was equal to V12. So same thing we have utilized here, that your VAO is equal to half of VAB plus V12. Similarly, VBO is minus of half VAB. Why minus? Minus has been taken because it is center tapped secondary. So we have plus, minus, plus, minus. Okay, so because of center tapped secondary, we have this minus VAC part plus VL, and we have this VBO as minus of half VAB plus V12. So we have VAO and VBO are the voltages applied across this D1 and D2. Okay, then what is our aim? Our aim is to obtain the output voltage. And what is the output voltage? VA dash B dash. So this output voltage is equal to the difference of the upper circuit and the lower circuit. I told you that these are 180-degree out of phase. Okay, so your VA dash B dash will be equal to VA dash O minus VB dash O. This is VA dash O, okay, and VB dash O. Then your we know that the voltage drop across D1 and D2, it is almost negligible. So your VA dash O and VB dash O can be taken approximately equal to VAO and VBO. So we can say that the output voltage VA dash B dash will be proportional to nothing but the difference of these two voltages, VAO and VBO. Okay, this you have to remember, that our output voltage is equal to the difference of these two voltages. Fine. So students, here in this slide we have proved that your output voltage will be proportional to the difference of the voltages VAO and VBO. Okay, and if you remember, and it is written on this slide also, our VAB is equal to JML1. Then we have V12 XC2. Okay, and then we had here R2 plus JX2. Okay, and what was X2? X2 was your J is as it is, it was XL2 minus XC2. This was our X2. Fine, XL2 minus C2, XC2. Okay, so now see, now the final part of explanation of this circuit. What is happening? If my input frequency is equal to the carrier frequency, okay, when my input frequency which comes here, that is equal to the carrier frequency, okay, means no modulation. In case of no modulation, I told you that both primary and secondary, they are tuned to same frequency in case of Foster-Seeley discriminator. Okay, so when my input frequency is equal to carrier frequency, in that case, means I am having the resonant frequency, and at resonance we know that inductive reactance is equal to capacitive reactance. So means XL2 equal to XC2, that will give me X2 0. If my X2 is 0, I am left with R2 only. So this X2 will become 0. I'll be left with R2. So when my input frequency is equal to carrier frequency, I get this. Okay. And if you express this term in terms of phasor, you get this. Okay. I hope you know this thing, that your if you have completely, imaginary part in your complex number, that means it gives you 90-degree phase. Okay, how do we represent a complex number in the help with the help of vector? Say if this is your real part A, and if this is your imaginary part B. Okay, if we have A plus JB. Okay, so if this is real part and this is imaginary part, okay, then your real or imaginary part have a phase a gap of 90-degree. Okay, so here what we have, once your X2, that is your imaginary part, is over, then if you carefully look at here, this is purely imaginary number. So obviously, since it is purely imaginary, if we have J can be written as 90-degree in phasor. So it becomes V12 X C2 M 90-degree. Okay, so in case your input frequency is equal to carrier frequency, your VAB is exactly 90-degree out of phase. Exactly 90-degree out of phase. Okay, and if so happens, then in terms of phasors or vectors, it looks like this. See, this is what happens. So what is happening here? We proved that, what we proved? We proved that my V12, see, we have to prove that my voltage applied to diode is sum of the primary voltage and corresponding half secondary voltage. This is what we had to prove. Okay, and see, this is my V12, that is primary voltage. This is my half VAB. Okay, and minus half VAB is 180-degree out of phase, means these two vectors are opposite of each other. Okay, this is V12. So these are two vectors. This is one vector, this is another. What will be the resultant of these two vectors? This is VAO. And what is VAO? VAO is sum of this, V12 plus half of VAB. Similarly, what is VBO? It is your V12 minus half of VAB. This also we had seen here. See, your VAO is half of VAB plus V12. Your VBO is this. So I'm showing these expressions with the help of phasors. That will help you in understanding. Okay. So, and there is 90-degree phase. This is 90-degree, exactly 90-degree. And this situation will happen when your F in is equal to FC. So if there is exactly 90-degree, then this will also be 90, because total is 180. It means the resultant VAO and resultant VBO, they will be exactly same. If you graphically look at VAO and VBO, both are same because their phase is same. VAB and half VAB and minus half VAB, they are exactly same. So if you subtract VAO and VBO, the output will be 0. Means when your input signal frequency is equal to carrier frequency, your output will be 0. Okay, then what happens if my input signal frequency is greater than carrier frequency? In that case, what will happen? V12 is as it is, In that case, if you look at this mathematical expression, we had this one R2 plus JX2. So now my phase is less than 90. Okay, less than 90 means resonance is not taking place. Okay, it means this will be some complex number. So if you represent complex number R2 plus JX2 with the help of phasor, this is what do we get? Mod of Z2 and then angle theta. Okay, because it is a some complex number because of which theta has come. Okay, and in the numerator part we have only the complex part. So if you convert this into phasor, you get V12 XC2 M angle 90. And you know that how do we solve this mathematically? The ratio of two complex numbers, this becomes total angle 90 minus theta. Your phasors are subtracted. So this is your, you can say, the magnitude part, and this is your phase part. Okay, so since your F in is greater than FC, okay, so F in is greater than XC means your XL2, that is J omega L, will be more than XC2. So if we have XL2 greater than XC2 means we have positive complex number. Okay, positive complex number means your positive theta. Okay, and net theta is 90 minus theta. And since we have this 90 minus theta, so this angle between V12 and VAB is less than 90. So since this is 90 minus theta, so this is minus half VAB. That is reverse of that. So it will come in 180-degree line with this. Okay, and if you take the resultant of V12 and half of VAB and angle 90 minus theta, your resultant will come out like this, VAO. This is VAO. And if you take resultant of this V12 and minus half VAB, this resultant will be this. And you can clearly see that the resultant VAO is larger than VBO. So obviously the output in these two cases will be positive, because VAO is larger than VBO. So when F in is greater than FC, okay, then your VAO will be larger than VBO. And why it will so happen? Because it is less than 90-degree out of phase. So graphically it will give us VAO more than VBO. Okay, and it will be less than 90-degree out of phase because for this case your XL2 will be greater than XC2. Okay, so this is how again when F in is higher than FC, your corresponding amplitude changes, positive value has been obtained. Okay, now the last case. In the last case, when your input signal frequency is less than carrier frequency, so in that case your X2, that is your XL2, will be less than XC2. In this case, in that case, this X2 part, this X2, this will be less than 0. Okay, so fine. So less than 0 means it negative. Okay, so we will have something, say R2 minus JX2. And because of this minus part, in the denominator, we will have angle minus theta. Numerator will remain as it is, that is your angle 90-degree. And if you solve them, your resultant angle will be 90-degree plus theta. That means the phase relationship between VAB and V12 in this case will be 90 plus theta. So this is your V12. This is your VAB, half of VAB. Angle is 90 plus theta. That's why it has moved away like this, 90 plus theta. Then you have to take minus half VAB in the opposite direction. If you graphically take the resultant, this resultant VAO, it will be smaller than this resultant VBO. It is very clearly seen. So here VAO will be less than VBO and net result will be negative. So it means if your input signal frequency is less than FC, your output will be negative. So when input signal frequency is equal to carrier frequency, your output is 0. When it is greater than carrier frequency, your output is positive. When it is less than FC, then your output is negative. This is how we have been able to convert our frequency changes into amplitude changes. And this we were doing in slope detector also, but the main advantage that we have got here is that our primary and secondary, they are both tuned to same frequency. We did not require more than one frequency, so that disadvantage has been overcome with. And this is how your Foster-Seeley discriminator work. And students, this proof is a bit involved one, so I will advise you people to go through this Foster-Seeley discriminator discussion once again, so that you are able to clarify yourself, and if there is any doubt, you can discuss in the next class. Okay.